so honored to be here today to present this second Professor Robert Hill Lectureship. And it's always great to recognize leaders who recognize the importance of supporting children with chronic health conditions and disabilities. And from what I've heard and read about Robert Hill, he was one of those special people. So I'm going to give you a bit of a whirlwind tour. I always try to stay on time, so my biggest challenge is going to be to make sure we have 10 minutes left over at the end of the hour to engage in discussion. But I'd like to give you a window of where I see some change happening in care and services for children with cerebral palsy as an example of children who have childhood onset disability. I won't do a formal land acknowledgement because Mia so kindly did that, but this is a picture that we did a little flag raising on Monday at Holland, Bloorview, and I thought, this is a powerful picture. I love the Canadian flag in conjunction with the flag recognizing every child matters. I have some peer-reviewed funding. That's a good thing. I have otherwise, I try to avoid any financial conflicts, so I can say I have no financial conflicts, disappointingly. I do, however, have some potential friendship conflicts, and I just want to acknowledge Professor Steve Miller, and I've worked together for a long time. I think you guys have a great leader in Steve for your Professor of Pediatrics. Sharon and I have worked together a long time and have really evolved. And I love that you picked up the win-win aspect because I do really think that's a powerful perspective. And then I'm also very close colleagues and friends with Maureen O'Donnell. But oh no, there's more conflicts that I have. Bob, I fondly remember ECS, Angie, Tim, Trevor, Anton, too many. So it's so fabulous to be here with people that I've known over many years. What I'm going to try to do today is I want to highlight early detection, a new clinical practice guideline that came out in 2017. I do think it is changing care and how we perceive, so I'll give you a little bit of insight there. There's a shifting landscape in looking at genomics of cerebral palsy, and I'll give you an overview of that. The most important part of my talk today is I'm going to use constraint therapy as an example of the power of a translational neuroscience network, hopefully get you excited about engaging in neuroscience. And then I'll finish off just by touching on the Dystonia care pathway that we've done. So I'm trying to do a lot, so I'm going to reorient you periodically in the talk in terms of where are we at in this talk. So this is the flow of my talk, and I'm a clinician first, so I'm going to embed it in a case study. So what do I mean by translational neuroscience network? I'll just give you a little bit of background. So this is really where a group of people come together and set common goals, but you have diversity in the group that is coming together. So we have our preclinical, our basic translational scientists, we have clinicians, we have clinician scientists, we have stakeholders, and we're all working together across a spectrum of activity that will drive the research field forward and eventually drive care. So basic translational research, hopefully to inform us and understand some of the basic mechanisms of action of some of the clinical interventions that we do. All the way to driving change through knowledge implementation science, because we know when it's left on its own, it takes close to 2 decades to bring a new discovery into practice. So I've been very fortunate to work in two neuroscience networks. And the first one I just want to highlight got its generation from Dan Goldovitz, who is from UBC. And he brought together a team and got a network centers.
No, why? That's cool. That's my to be dressed, but or to be on like if I make it there, I know I'll be satisfied. I'm probably gonna be asked.
If there's a group who has their microphone on, could you please mute yourselves?
Thank you. I see they're paying careful attention. So this is a group that brought together a team across Canada to focus on cerebral palsy. And then also have been fortunate to receive funding from the Ontario Brain Institute, and over a decade have been working with a group of people from across health centers in Ontario. Now, one of the things that we have done is we've created a large clinical database. And, you know, sometimes databases can be a little bit boring, but this one has been quite useful. So we now have 1,000 children in our database, and we have different platforms. So we collect information on clinical risk, we collect information on neuroimaging, we collect saliva from the child and the parent, and we do DNA extraction so we can drive genomic research. We get a picture of their neurodevelopmental profile, but we are also strengths-based, and we look at participation and psychosocial aspects. So in our CPNet neuroscience network, the clinical database has helped us to drive our science. Now, I'm focusing on translational neuroscience, so we also have a basic science component. And here we're using murine or rodent models of cerebral palsy to try to look at and understand basic mechanisms. So here's our case study. You're a pediatrician, you've got a consultation, you're seeing John. He's 9 months old, and he's been referred because of early handedness. Parents report that he's sitting, plays with toys, more with his left hand than his right, but they're not concerned. There's a family history of left-handedness. And you do a neurodevelopmental screen. The child grabs a toy with a pincer grasp in the left hand and a palmar grasp with his right hand. So I'm moving to early detection here. So one of the stakeholder messages that we got when we first formed CPNet is they were really frustrated with the late diagnosis of cerebral palsy and hemiplegic cerebral palsy. They wanted us to do activities where we drove home the message: hand preference is a signal if it develops too early. The other thing that I want to drive home is that when we're young, all our movements are very symmetrically based. So if you see differences or asymmetries, that should also be a red flag for you. So here's a beautiful site that talks about regular child development. This is a little 6-month-old video and really showing bilateral hand use. He's eventually going to grab that cube, and he does it with a radial palmar approach. Right to the mouth, of course. Going to bring the other hand in and mouth it. And then we're going to look to see how he grabs the other cube, because we want to see symmetry. And there we go. So in contrast, now this video is a little bit older than 9 months, but it's a video that I have. So we're doing a quick screen, beautiful pincer grasp with the left hand and a palmar grasp with the right hand. So clear asymmetry. Should you make a diagnosis of cerebral palsy? So just a show of hands, what did you typically diagnose cerebral palsy? Less than 6 months? Put up your hand. 6, okay. We got a few hands. Oh, yeah, oh, okay. 6 to 12 months. Okay. 12 to 24 months. Over 24 months. Okay. I know I was taught as a pediatric resident that you should not diagnose cerebral palsy before 2 years of age because the neurologic examination is changing too frequently. However, you've been keeping up on your reading and you make a clinical diagnosis of high probability of unilateral spastic hemiplegic cerebral palsy, even before you get the MRI back. So age of John at initial diagnosis is 9 months. Congratulations. You have met the early detection of CP clinical practice guideline, where the aim is to make a clinical diagnosis of cerebral palsy before 12 months of age. So a real shift in our practice. Literally, I was taught, don't make it before 24 months. So here's where we're sitting in Canada. We have an average age of CP diagnosis at 19 months. So it's less than 24 months, but it's shy of the 12 months. In 2017, this early detection of cerebral palsy clinical practice guideline came out in JAMA Pediatrics. I can tell you it was controversial, and the lead author took a lot of flack. That was Iona Novak. I was very pleased to be part of this and part of this publication, and I do see it actively shifting practice, particularly in neonatal follow-up care. So why do we want to do early detection? There is a whole body of neuroscience that tells us that the earlier we can intervene, the more impact we can have with that intervention. So an early detection diagnosis allows you to do an early referral. So let's just do an overview quickly of this clinical practice guideline. So things change. What I learned in pediatric residency is now behind the times. It's a late diagnosis if you're between 12 to 24 months. This clinical practice guideline was brought about by using GRADE. GRADE is a way to critically evaluate literature, and it's the top way. It came out of McMaster University, so Bob Armstrong will be familiar with GRADE, and the WHO has now embraced GRADE as the way to bring evidence into practice. So it's gaining steam. This clinical practice guideline uses GRADE. You can make strong or conditional or strongly against recommendations. So here's some of the key recommendations. You should make a diagnosis of cerebral palsy as early as possible. Here's the win. This is why I think this guideline has taken off. As I said, well, if you don't feel comfortable making that diagnosis, say high risk. Now, we've started to shift to saying high probability because there's been a little bit of pushback on that risk, which is a negative term. Probability is a more neutral term, so we're starting to use high probability. How do you make this diagnosis? You embed standardized assessments into clinical care where you're following children with risk, children who are born preterm, children who have neonatal encephalopathy, children who have congenital malformations or birth defects, or if they've had an NICU admission. So the neonatal follow-up care is really the home to these standardized assessments, and they consist of the general movements assessment. This is a movement of looking at children under 18 weeks of age, and was developed by Precel, who was a neurologist from Italy. General movements is one. Brain imaging, MRI, is another. And then the third one in the middle is a standardized neurologic examination called the Hammersmith Infant Neurologic Examination. So what is this general movements? It's a little bit of a hard test to understand, but it looks for fidgety movements at around 12 weeks of age. Fidgety movements are normal. The absence of fidgety movements are abnormal. In the absence of fidgety movements, if you have one of those risk factors, it's highly predictive of future development of cerebral palsy, over 95%. Fidgety movements are important. And then, or the absence of fidgety movements is the signal. And the other signal is the presence of cramped, synchronized movements. So compared to that previous video where there was a lot of free-flowing, fidgety movements, this baby is not moving as much. These videos look simple to present to you. It takes a lot of training to get the team to be able to interpret the videos well. And that's where a lot of the effort is on integrating the general movements into neonatal care and neonatal follow-up care. Those who've worked with me know I'm a huge fan of the Hammersmith Infant Neurologic Examination. It, in contrast to general movements, is teachable. You can do it in your clinical practice in 5 minutes, and it's just a beautiful way of standardizing your exam. So if you're a pediatric resident, really encourage you to learn the Hammersmith Infant Neurologic Examination. The other thing I will say here is that the Hammersmith Infant Neurologic Examination is much more sensitive at picking up hemiplegic cerebral palsy than the general movements assessment. It picks up asymmetries beautifully. And so if we're trying to get early detection of our commonest type of cerebral palsy, which is hemiplegic cerebral palsy, present in close to 40% of our kids with CP now, the Hammersmith is the way to go. We had great presentations by students earlier today, and one of them was presenting on early detection under the supervision of Moore and Ram. And one of the points that was made is, okay, we have children presenting with cerebral palsy in our neonatal follow-up. We should be able to do a good job of diagnosing those. But another point I want to make is about 50% of our children will actually present in primary care context. So we have to use different strategies than the general movements and the Hammersmith. And I've been fortunate to work with Annette Maenemer. Zachary Boychuk is a PhD student that worked with Annette. And we've been doing some work on the early detection in the primary care context. And there's been some beautiful tools that are going to be embedded in the Rourke-Well child care based on this work. And I think that will help to facilitate early identification through the primary care context. So if we look at this one, this is one of the early detection primary tool pictures where we see a clear hand preference and the atypical development slide. So back to our case study. You've made this diagnosis of high probability of cerebral palsy. You've diagnosed unilateral spastic right hemiplegic cerebral palsy. And the parents say, okay, well, what investigations and treatments are you going to recommend? You have read the early detection clinical practice guideline, and you know that you need to do both investigate and refer for therapy at the same time. Congratulations. So you are in an MRI, and this is the picture that comes back. You certainly have an asymmetric lesion, and your neuroradiologist interprets it as a deep parenchymal hemorrhage. And he says, or she says, better rule out Col 4A. You rush to Google and you say, Col 4A, I think I've heard about that. So are there additional investigations that you should do? So I'm now transitioning to genomics. So let me give you a little bit of background. Contributions from genetic variation to the clinical phenotypes of CP increasingly are being recognized. I think some of the genomics work in neurodevelopmental disorders like autism and intellectual disability were really the thing that was driving us to look at genomics and cerebral palsy. But ironically, we are getting much bigger hits in cerebral palsy than we are in many other neurodevelopmental disorders. So the majority of studies in cerebral palsy to date have been either microarray copy number variation studies or exome sequencing. However, whole genome sequencing allows you to look at both SNV, single nucleotide variations, copy number variations, rare structural variants, but also importantly, mitochondrial variants. And so why are we interested in mitochondrial variants? Just to give you a little bit of background, first of all, they can be detected by whole genome sequencing. So much of the literature to date has been exome sequencing, which has ignored mitochondria. They're inherited differently. They're inherited from the mother. And we all have some heteroplasmy in our mitochondrial DNA. Well, what does heteroplasmy mean? It means there's a bit of variation. You've got your regular mitochondrial DNA, but you have some small proportion of a rare variant. If you see a big increase in that mutant variation in your mitochondria between the mother and the child, that's suggestive that there may be a problem with the mitochondria and that the mitochondrial variant in the DNA may be contributing to the disorder. So with that, we utilized the power of our CPNet clinical database to do a genome study in a representative population of children with cerebral palsy. And we were rewarded by our methodology with a publication, a recent publication in Nature Genetics, where we have looked at comprehensive whole genome sequencing analysis to really try to understand in a representative sample of children with cerebral palsy what is contributing to genetic etiologic risk. And you'll see that I'm positioning it as genetic etiologic risk rather than a diagnosis. So the diagnosis of cerebral palsy is a clinical diagnosis. So where the genomics is helping is it's giving us information on what might be contributing to the risk of that child developing cerebral palsy. Just a little bit on methodology. We had 323 families. 2/3 of them were from CPNet. 1/3 were from our national CP registry. So we had deep clinical phenotyping information on the children. And then importantly, we had a control group where we could look at a de novo gene burden analysis in typically developing children and compare it to our children with cerebral palsy. We did whole genome sequencing, which is state of the art, and then used a clinical database where we had clinical risk factors, neuroimaging, genomics, and neurodevelopmental information on the children. So here's the main results. 70% in green, no variance. Well, the flip side of that is 30% had some variance. 18% were variants of uncertain significance. So there's a change happening. We don't have enough information yet to say that it's pathogenic or likely pathogenic. So we had 11%, so 1 in 10, that had a pathogenic or likely pathogenic variant. Most commonly single nucleotide variants, about 6%. 3% had copy number variants. That's where we have a section of the genomic material that's either been deleted or duplicated and can encompass multiple genes, so a little bit harder to interpret. And then one of the interesting things from this work is we had 5 children, 1.5%, who had mitochondrial variants. So we found that quite interesting because that had not been detected before. So our most frequent SNV was COL4A. And it is where you have a problem with your collagen that puts you at risk to have deep parenchymal hemorrhages. So linking back to our case study, if it's a unilateral hemorrhage, you're going to present with hemiplegic cerebral palsy. If it's a bilateral hemorrhage, you may present with forelimb involvement. The mitochondrial, don't worry about reading this slide. The blue circles are, I wanted to just show you the information on the heteroplasmy. So each of the children who had mitochondrial mutation that was heteroplasmic, they had an increase in the heteroplasmy between the mother and the child. And that's, again, I'm not a mitochondrial expert, but that's highly suggestive that the mitochondrial mutation is contributing to the disorder. When we look at the disorder that the variation was linked to, it was linked to MELAS, mitochondrial encephalopathy, lactic acidosis, and stroke-like episodes. So isn't this interesting that although if you have recurrent seizure strokes, it will look like a progressive disorder, you have a link between this neurodisability and the CP presentation. So for the clinicians in the audience, you're thinking, okay, well, what are the clues that I can get to think, when should I be ordering genetic testing in cerebral palsy? Here's the CP phenotypic features that were associated with having a pathogenic or likely pathogenic variation. So if you had a normal brain MRI, make sure you refer to genetics. If you have an intellectual disability, many of these children are having genetic workups anyways. So that was also a marker that you might find something in the CP avenue. We had more genetic findings in children who were born at term compared to preterm, and then consanguinity. The brain MRI is, in addition to having a normal brain MRI, neuroradiologists are now aware of the COL4A picture, so they'll often flag that. So that, of course, is to do a genetic, if you have a brain malformation, there's also an increased chance of detecting a pathogenic variant. Just in terms of if there's any cynics in the audience, there's never cynics in audiences, I know, but this was cool information. This is a gene burden analysis. And so there's a clear link in our pathogenic, likely pathogenic variants and genes that are very important for early brain development. So definitely there is a story evolving around genomics and cerebral palsy. Now, we're not at the stage where we're saying you have to do a genetic workup for each child you see with cerebral palsy. We're at an evolving, who should we be working up? I do think it will impact, there'll be more children that we're referring for genetic workup with cerebral palsy. When we look at all our CP cohorts, we always find children with HSP, hereditary spastic paraplegia, that have a different pattern than cerebral palsy in some cases. We also find, like in our case series, we had one child who had a dopa-responsive dystonia. That's a really important diagnosis to make because these children respond to levodopa. So the testing can inform drug therapeutics. It certainly can help enhance the understanding of the child that you're seeing in front of you. It's going to shift our spectrum on the disorder of cerebral palsy or the disorder of HSP. I think we're going to increasingly find many children with the HSP diagnosis that follow a static course. And so do they really have cerebral palsy? And it is shifting and creating a little bit of a perturbation of, well, if I have a genetic diagnosis, does that mean we take the clinical diagnosis of cerebral palsy away? So it is having some clinical impact. There's also the impact on the family of having a positive genomic finding. Why ultimately am I excited about genomics is I think it may help us to drive drug therapeutic development. We have not had any new good drugs for cerebral palsy for a long time, and I think it will help to start to open up that window for us. The way of the future is large international cohorts, and we're part of an international genomics consortium. Okay, let's go back to our case study. So we've got a child with right hemiplegia. Parents really want to know what treatments you would recommend. You respond. You're going to make an immediate referral for consideration of early intensive manual therapy, baby CIMT. Congratulations, you're following the clinical practice guideline. All right, so I'm now going to move into talking a little bit about the neural mechanisms of constraint utilizing this translational neuroscience network. This is a really fun diagram. It's a summary of all the evidence of our interventions for cerebral palsy. And the higher up in the green, the more you should be doing these interventions. And the size of the bubble represents the evidence. I don't have a pointer, but the CIMT bubble is one of those big green bubbles. So whenever we look at constraint therapy, we see an effect. That suggests to us that this is an opportunity to try to better understand the underlying brain signal that we're creating with constraint and perhaps understand mechanisms. So what is constraint therapy? I know all my videos work because I tested them before. Oh, this one's frozen. Well, you can get at what I'm trying to show here. So what we do is we constrain the less affected hand to force the use of the hemiplegic hand. And we do focused motor and sensory training with the hand. Oh no, there we go. So here's a child pre-constrained. He's ignoring his right hand, really having trouble using it. And then here's the same task after he's able to incorporate the hand and do the task. So we asked, what are the potential underlying neural mechanisms in constraint? I'm going to give you some background so that you can follow the research that we've done. So we control our left hand with the right side of their brain. We control our right hand with the left side of our brain. We call that contralateral control. We're all highly contralateral. If we looked at a functional MRI, we would be predominantly contralateral, and our laterality index would be high. It would be over 0.9. The laterality index is balancing the activity in both hemispheres. We get information from the structural MRI, and if you look at that second column, those yellow blobs, in a person who has hemiplegia, we have evidence of activity on both sides of the brain. So there's some contralateral, but there's also ipsilateral control. We can get information from resting state networks, and this is a picture of the resting state network, our sensory motor network. And a resting state network is where networks are connected. So we have a very strong bilateral resting state network. We get information from magnetic encephalography, and this gives us similar information. I wish I had a little pointer, but you get power information from a very isolated region of interest. So if you can read the power reads, they're both about 2.3, 2.4, but it gives us a breakdown of motor planning pre-zero, and then sensory information post-zero. So it starts to help us tease out motor from sensory. Here's a functional MRI, individual with a large MCA infarct, and they've shifted the control of their hemiplegic hand almost completely to the ipsilateral side. to the premotor and supplementary motor cortex area. And then the two more pieces of information. The white dots at the bottom represent contralateral activity. And the only individuals with hemiplegic cerebral palsy that have good hemiplegic hand control are those who are still controlling their hand contralaterally. So there's a suggestion that contralateral control is superior to ipsilateral. We got information from our adult neurology colleagues. They started to do stimulation and recognized that if you had a stroke, the non-stroke hemisphere of the brain started to suppress the side that had stroke. And by doing a stimulation, they could rebalance that hemispheric activity and provide further fine motor output. So with that background, what are the potential underlying neuromechanisms in constraint? So this is one of our earlier studies. And if we look at the laterality index pre-constraint, you'll see it's negative, minus 0.25. That means predominantly that person is controlling their hand by their ipsilateral hemisphere rather than their contralateral. It's a negative. After constraint, we see that laterality index and we see the fMRI has shifted to the area of injury. It's a positive 0.43. So that tells us that the constraint is starting to drive activity back into the contralateral side. And it was maintained. Interestingly, it increased. Every time we look at this, it's increasing at 6 months. So it's back to 0.72. Again, you and I, we would be at 0.9 or above, but 0.72 is much closer to contralateral control than minus 0.25. Here's our MEG work. 2 baseline values showing energy, power from the region of interest on the injured side. They're both the same at baseline, 2.3, 2.2. After, we've driven up activity. So that's the same message that I said before, except 4.4. We've driven up contralateral activity. But what's really interesting is if we look at the red MEG line, the change was in the sensory. So this gave us a suggestion that not everything was driven by motor planning, that it may be sensory awareness that was helping the individual use their hand better. So we did a deeper dive into the sensory changes following constraint. The top graph shows you the normal somatosensory evoked potential in the primary S1 area of the ipsilateral non-injured hemisphere, both pre and post constraint. Pre is blue, post is red. We haven't injured that ipsilateral hemisphere with constraint. But look what's happened in the contralateral hemisphere. That's the bottom one. So pre-baseline, that somatosensory evoked potential is really abnormal, very flat. And look at how much improvement we've seen in the somatosensory evoked potential in the red post. And most of this has happened at the P100 wave form. So what this suggests to us is that not only are we driving motor control back into that contralateral injured hemisphere, we're improving sensory processing. We then wanted to look at that resting state network and see if constraint helped to rebalance that hemispheric activation. So that's what this study was about. Remember I showed you that picture where our resting state networks are very bilateral? Look at where we are pre-constraint. We have no activity happening in the sensory network pre. And then look at post-constraint. We're starting to rebalance that sensory motor network. So there's a suggestion that we may be releasing that hemispheric inhibition that's happening in the normal hemisphere. And then this is just a graph of our findings showing that in our case study, we were seeing that approach of a balanced resting state network. And finally, this is research from our CPNet translational neuroscientist basic science team. And I won't go through all the details here. I have to say they were innovative. They figured out the rodent model of hemiplegic cerebral palsy. They did a congenital injury, and then they provided constraint by using Botox and injecting the unaffected limb to constrain it. They tried to put little casts on first, but the mother rats were too good at eating off the little casts. And so they used the Botox. So the bottom line here is, with constraint, they've shown the underlying mechanism, or one of the underlying mechanisms, is inducing an endogenous oligodendrocyte response. That's pretty exciting. So by looking and doing this deep dive, we now know we have some brain signal for constraint. So what have we found out? That we're driving some improvement in sensory processing, that we are driving control back to the contralateral motor. We're rebalancing that hemispheric activation, and pretty cool, we're inducing endogenous stem cells, baby oligodendrocytes, to make that connection between the corpus callosum, but also the corticospinal tract healthier. So, case study. Parents want a referral to baby CMT program right away, please. Oh, this is not true for UBC, but there are no baby CMT programs in your area. So in many areas of Canada, we had started to get constraint programs going in the country, but baby constraint was well behind. So I want to move now to a knowledge implementation science project that we've done. So the basics, we're driving Hammersmith into neonatal follow-up because we know it's excellent at picking up asymmetry. We're facilitating early referrals, and we're supporting occupational therapists to learn how to develop and provide baby CIMT. We use the knowledge to action cycle to drive this change. I won't go through a lot of that, but I will say the pandemic helped us out. We started doing a lot of Zoom-based webinars, and we really were able to engage a lot of people across Canada. And we also set up monthly community of practice meetings through Zoom. And these were both really great strategies. We started in Ontario. We moved to Canada. Here's our basic result is for baby CIMT, over the time period of the study, we had 56 referrals to our teams. This is across Canada. And the average age of referral, 7.8 months. I'm so pleased with that. So that's a huge win. And linking back to the neuroscience, why is that important? Kathleen Friel, one of a real luminary neuroscientist in the field, has shown that in a cat model, if you can do early intervention, you maintain and support a connection of the corticospinal tract at the spinal interneuron level. And the 12 to 14 weeks in the cat corresponds to 3 to 6 months in the child. If they did constraint after that, they still got some improvement, but not nearly as much improvement. And so it really suggests to us that baby CMT is really important. And if we can get it done early, we're going to get better outcomes. That is supported by a large randomized trial that's not yet published, coming out of Australia, where they found that children were randomized to baby CMT or a program called bimanual. They both improved, but the key to most improvement was getting the referral before 7 months of age. So I just have a few minutes left. I'm going to do a little whirlwind bladder part of my talk. So case study again, John comes back to you, parents are saying, listen, things are okay, but I think he's getting stuck in painful postures. You diagnose dystonia, you think, I think there's a new AACPDM Care Pathway on dystonia. I'm going to read it. So let's do a little whirlwind tour. I have a quick video. This is a child with generalized dystonia, but certainly we see hemidystonia, where they really get stuck in postures. We know from a large study we did of a representative group of children in our clinics at Holland, Bloorview. We tested over 400 children, that a quarter of them were in moderate to severe pain, restricting activities. And we did a physician diagnosis of the cause of the pain, and dystonia and hip subluxation were the two common causes of pain. So we know dystonia can cause pain. There's a lot of confusion about recognizing and treating dystonia. And so we felt there was an opportunity to do an international group to develop a clinical practice guideline. We went through the grade process. It's painful. We do have a final product. It's up on the American Academy website. And I encourage you to visit it. Section 1, you can read it in 5 minutes and you get a bit of an overview. Section 2, for those who are keen, you can do a deep dive into our systematic review and clinical practice guideline. And Section 3 gives you practical tools like, how do you diagnose dystonia? So in our clinical practice guidelines, Section 1, painful focal postures, you might consider botulinum toxin. So in summary, I've given you a vision for CP research driven through translational neuroscience networks with common goals. I've discussed the potential for neural mechanisms of action of constraint therapy as an example. I think we can do deeper dives into other things. It was a good place to start because we knew we were getting a strong signal clinically. I've discussed the importance of early diagnosis and genetic etiologic risk for CP, and discuss the need for knowledge implementation science to drive the change that you want to see. So I would like to thank you for your attention today. I've got a division picture up there. I've got my lab picture up there. Most importantly, I've got my family picture up there, and picture of my parents. And just really like to thank Sharon and Mia and Bob and the whole team for inviting me here for this lectureship. Thank you.